From the first crude models to the modern marvels we see today, countless innovations have been introduced to improve internal combustion engine performance. Yet despite all the advancements over the years, which include massive scholarly works, incredibly precise CNC machining, space-age alloys, and advanced electronic management systems, the thermal efficiency of most IC engines remains frustratingly low, typically below 40%. One extraordinary example is the Formula One engine. For example, the 1.6-liter V6 turbo hybrid in the Mercedes-AMG W11 has achieved around 52% efficiency. This is despite its $11 million price tag and a research and development budget that could rival the GDP of some countries. If a high-tech marvel like that struggles to cross 50% efficiency mark, it begs the question, why can't we make IC engines more efficient? Why, after over a century of development, are we still operating at such low levels of thermal efficiency? Today, we'll explore the reasons behind this fundamental challenge. Subscribe to the channel. It's important to note that when we talk about engine efficiency, we're not referring to miles per gallon. Instead, we're discussing thermal efficiency, which measures how effectively the engine converts the energy from fuel into useful work. Internal combustion engines have come a long way since their inception, steadily improving efficiency over the decades. In the last few years alone, gasoline engines have been hitting around 40% thermal efficiency, thanks to advancements in lower friction components, better air-fuel mixing, and advanced valve timing control. Toyota has developed the Dynamic Force engine, which reaches 40% efficiency in standard IC engine mode and 41% in hybrid mode. Nissan has come up with a prototype engine that could achieve 50% efficiency, but only in a very narrow operating range. Diesel engines have also reached impressive milestones. The Volkswagen 3.3 V8 TDI from the early 2000s hit 41% efficiency, while large marine engines are currently leading the pack, achieving up 55% efficiency. Stationary gas turbines used in power generation go even further, achieving around 60% thermal efficiency. These are designed to operate under optimal, consistent conditions, unlike automotive engines, which need to function across a wide range of speeds and loads. The theoretical limit. When it comes to improving the thermal efficiency of internal combustion engines, we are fundamentally constrained by the laws of thermodynamics. The theoretical limit on how efficiently any heat engine can convert heat into mechanical work is governed by the Carnot cycle, named after the French physicist Sadi Carnot. This cycle defines the maximum possible efficiency a heat engine can achieve when operating between two temperature limits, often called the hot and cold reservoir. The temperature difference between these high-temperature heat sources and the low-temperature heat sink determines the efficiency. The larger this temperature difference, the higher the potential efficiency. However, in real-world applications, achieving this ideal efficiency is far from simple. The Carnot efficiency formula, where Tc is the cold temperature and Th is the hot temperature in Kelvin, shows that no engine can be 100% efficient because the cold side can never be brought down to absolute 0 Kelvin, and there is always some loss of heat. In practice, this means that the best we can do is strive to maximize the temperature of the hot side, typically the post-combustion gas, and minimize the temperature of the cold side, usually the ambient air. However, this is where we hit a roadblock. The materials used in engine construction, like aluminum, steel, cast iron, and even titanium, have limits on how much heat they can tolerate. For example, gasoline burns at approximately 2200 degrees Celsius, but most engine components begin to fail well before reaching that temperature. Additionally, engine oil starts to degrade and lose effectiveness above 150 degrees Celsius. As a result, we must remove a significant portion of heat to prevent the engine from melting down or the oil from breaking down. Another challenge is that engines must operate under a wide range of loads and speeds, which is the opposite of what is needed for maximum thermal efficiency. In an ideal world, an engine would work within a narrow temperature band, but for cars, the engine must be flexible, leading to significant inefficiencies. To further illustrate the limitations, consider that systems like large power plants, which utilize elaborate heat management systems, such as Clausius-Rankine cycles. They come close to the Carnot efficiency by preheating the working fluid and using multi-stage processes. and using combined cycle gas turbines, the efficiency can reach up to 60%. However, such intricate systems are impractical for automotive engines due to space and complexity constraints. A car engine simply can't accommodate the extensive piping and preheating stages that power plants use, so additional energy is lost as waste heat. Formula One engines achieve over 50% thermal efficiency using pre-chamber combustion. Pre-chamber combustion enables the engine to operate closer to the flame point of the fuel, allowing for more efficient combustion. However, this is far from practical for everyday use. The immense wear and tear it causes means that an F1 engine is designed to survive only a few thousand kilometers before it needs to be replaced. It also requires high-end materials, like ceramic parts and exotic alloys, and extremely tight tolerances, so much so that the engine has to be carefully preheated before starting, or it will jam. While these high-efficiency engines are impressive, they are impractical for everyday use due to wear, cost, and operating conditions. For the average car, 40% efficiency is about as good as it gets, for now. Thermodynamic cycles and engine losses. The Carnot cycle represents the theoretical upper limit for engine efficiency. However, in real-world applications, most engines use variations of the Otto cycle for gasoline engines or the diesel cycle for diesel engines, which have lower efficiencies compared to the Carnot ideal. While certain designs, like the Atkinson cycle used in hybrid cars, slightly improve efficiency by optimizing the piston's motion, these cycles still fall far short of the theoretical maximum. It is difficult to analyze the actual cyclic engine process as it is quite complex. That is why the ideal air standard cycle is used. In actuality, the air-fuel mixture enters the cylinder and mixes with leftover exhaust gases from the previous cycle. This mixture is compressed, combusted, and turns into exhaust gases like CO2, H2O, and N2. After expanding, the exhaust is released. Because it's an open cycle with changing composition, it's hard to analyze, so we simplify it using an ideal air standard cycle. In air standard cycle, the gas mixture in the cylinder is treated as air throughout the cycle, making analysis easier. Further, the air is treated as an ideal gas, allowing the use of basic ideal gas laws like PV equals MRT in the analysis. The open cycle is treated as closed, meaning exhaust gases are considered to re-enter the intake, simplifying calculations. Combustion is replaced by a heat addition term and exhaust by a heat rejection term, matching their energy values. Various engine processes are assumed to be reversible and idealized. Intake and exhaust strokes are considered at constant pressure. Compression and expansion strokes are treated as isentropic, nearly frictionless, and adiabatic. Combustion is approximated as constant volume for SI engines, constant pressure for CI engines, or a mix. Exhaust blowdown is approximated by a constant volume process. The air standard cycle associated with gasoline engines is the Otto cycle. Only the compression ratio is needed to determine the thermal efficiency of the Otto cycle at wide open throttle. As the compression ratio increases, the thermal efficiency improves, meaning more energy from the fuel-air mixture is converted into useful work. This efficiency is referred to as the indicated thermal efficiency. Mathematically, it is given by this equation, where Rc is the compression ratio and K is the ratio of specific heats. While the air standard cycles like the Otto cycle offer a theoretical framework for understanding how heat energy is converted into mechanical work in gasoline engines, various factors limit the efficiency of actual engines. Engines operate on an open cycle with changing gas composition and mass flow rates. Air standard analysis assumes all fluid is air, but real engines deal with air mixed with fuel, and the gas's specific heats vary with temperature. Heat losses during combustion lower actual peak temperature and pressure. Compression and expansion aren't fully adiabatic. Heat is lost, reducing efficiency. Incomplete combustion. The time available for the combustion process of an engine cycle is very brief, and not all fuel molecules may find an oxygen molecule with which to combine, or the local temperature may not favor a reaction. Consequently, a small fraction of fuel does not react and exits with the exhaust flow. It typically has values in the range 0.95 to 0.98 when an engine is operating properly. Exhaust blowdown isn't instantaneous, leading to energy loss. Intake valves remain open past bottom dead center, delaying true compression. Valves take time to actuate, requiring early opening and delayed closing for optimal performance. But interestingly, Air Standard Auto Cycle Analysis provides fairly close estimates of real engine temperature, pressure, power output, thermal efficiency, and mean effective pressure. Adjusting variables like inlet temperature, pressure, or compression ratio in the analysis can predict real-world changes. Literature shows that over a wide range of operating variables, the indicated thermal efficiency of an actual gasoline four-stroke cycle engine is around 85% of that of Otto cycle. In addition to the thermodynamic losses of Otto cycle and incomplete combustion, we have pumping and friction losses. Pumping losses, the work required to induct air and fuel into the combustion chamber and expel exhaust gases, is referred to as pumping losses, and it is given by gas exchange efficiency. Pumping losses reduce the efficiency further. Friction and parasitic losses. Friction between engine components and the work needed to drive auxiliary systems, such as oil and coolant pumps, further reduce the amount of energy available to do useful work. This is given by mechanical efficiency. Finally, after accounting for all losses, we can determine the brake thermal efficiency by combining indicated thermal efficiency, combustion efficiency, mechanical efficiency, and gas exchange efficiency. Efficiency and performance improvement endeavors. Multiple strategies are tried for reducing losses and improving performance, targeting mechanical motion, combustion, optimizing the process of air-fuel mixture induction, and the exhaust, friction reduction, heat management, and more advanced cycles. Combustion optimization. These technologies focus on making fuel burn more efficiently and extracting the maximum energy from each combustion cycle. These are higher compression ratios. Operating an engine at higher compression ratios increases the efficiency of energy conversion as more energy is extracted from expanding gases. However, higher compression ratios require higher octane fuels to prevent knocking. The Atkinson cycle and Miller cycle take advantage of this by utilizing variable cam timing to extend the expansion phase. The Atkinson cycle uses a smaller compression ratio than expansion ratio, making the process more efficient by cooling the exhaust gases before they are released, thus wasting less energy. This cycle is commonly used in hybrid vehicles like the Toyota Prius. It increases the expansion ratio in the engine by keeping the intake valve open longer during the compression stroke, making the engine more efficient and ideal for low-demand driving situations. The Miller cycle uses a supercharger and delays the closing of the intake valve to reduce pumping losses. This improves thermal efficiency, offering better fuel economy without compromising power. Direct fuel injection. Direct fuel injection injects fuel directly into the combustion chamber rather than the intake manifold. This precise fuel delivery improves combustion efficiency by well-atomizing fuel, resulting in more power and better fuel economy. Common rail direct injection, or CRDI. Diesel engines, common rail direct injection uses extremely high pressure to inject fuel into the combustion chamber. This leads to more efficient combustion and reduced emissions, making it a staple in modern diesel technology. Lean burn engines. Lean burn engines use more air than fuel in the combustion process, improving fuel economy. However, they require advanced emissions control systems to keep pollutants like nitrogen oxides in check. This method was used to improve fuel economy in the past, but modern engines must operate at a stoichiometric air-fuel ratio to allow the three-way catalyst to reduce emissions. The development of a lean nitrogen oxides catalyst has enabled engines to run lean while maintaining emissions compliance, significantly increasing efficiency. HCCI, Homogeneous Charge Compression Ignition. HCCI technology combines features of gasoline and diesel engines. It compresses a homogeneous air-fuel mixture until it ignites on its own, offering diesel-like efficiency with gasoline-like performance. Chamber modifications. Modifying the combustion chamber design can improve air-fuel mixture rates, leading to more complete combustion, especially with alternative fuels like biodiesel, and contribute to reduced emissions and better thermal efficiency. Optimized cylinder design. Shorter stroke pistons can reduce quenching of the flame front on the cylinder walls, thereby allowing for more complete combustion. This also decreases friction losses, but it increases heat transfer loss. On the other hand, long-stroke engines increase the piston's stroke relative to its bore, improving thermal efficiency by allowing more expansion of the gases. Due to less surface area in the combustion chamber, it also results in less heat loss. However, the longer stroke results in higher piston speed and higher friction losses. In contrast, A square engine design, where the bore and stroke are roughly equal, aims to balance the benefits of both short and long stroke configurations. Square engines typically offer a compromise between the high revving characteristics of short stroke engines and the torque advantages of long stroke engines. Most modern automobile engines are near square, with some slightly over square and some slightly under square. This is dictated by design compromises, required engine characteristics, and the technical philosophy of the manufacturer. Air induction and intake management. This group of innovations include technologies that improve how air enters the engine, helping boost power and efficiency by ensuring better air intake. Turbocharging. Turbocharging harnesses exhaust gases to drive a turbine, which forces more air into the combustion chamber. This not only boosts power output, but also improves fuel efficiency by enhancing the engine's volumetric efficiency. Supercharging. Supercharging, on the other hand, works similarly to turbocharging, but is powered by the engine's crankshaft. It forces more air into the engine, boosting performance and power. Though not as efficient as turbocharging, it provides immediate power without the lag often associated with turbos. Intercooling. Intercooling plays a vital role in both turbocharged and supercharged engines. It cools the compressed air before it enters the engine, making it denser and improving combustion efficiency. This cooling process helps the engine generate more power while using less fuel. Variable valve timing and lift. Variable valve timing (VV) optimizes the timing of valve opening and closing to improve performance and efficiency at different engine speeds. Some famous examples include Toyota's VVTi, Honda's VTEC, and BMW's Vanos. Meanwhile, variable valve lift (VVL) controls how much the valves open, improving airflow and combustion efficiency. Nissan's VVL and Audi's valve lift are excellent examples of this technology in action. Fuel efficiency and power management. These focus on optimizing how much fuel the engine uses and managing power output to ensure the best balance between performance and economy. Cylinder deactivation. Cylinder deactivation technology shuts off some cylinders when full engine power isn't needed. For example, GM's active fuel management and Chrysler's multi-displacement system reduce fuel consumption by running the engine with fewer active cylinders during light loads. Engine downsizing. Engine downsizing is the latest trend in engine design. It involves using smaller engines, often with turbochargers, to provide the power of a larger engine while consuming less fuel. This helps reduce emissions and improve efficiency. Eco mode driving settings. Eco mode optimizes the engine's performance by adjusting throttle response and shift points to prioritize fuel economy over power, making it easier for drivers to save fuel during everyday driving. Electric water pump and electric power steering. Replacing traditional belt-driven water pumps, the electric water pump reduces drag on the engine by operating only when needed, and electric power steering eliminates the need for a hydraulic power steering pump that runs off the engine. This reduces engine load, improving fuel economy. Lightweight engine materials. Using lightweight materials such as aluminum and composites in engine construction reduces the vehicle's overall weight, improving fuel economy and performance. Reducing frictional losses. Lowering friction in the intake and exhaust manifolds can improve airflow, reducing resistance and increasing efficiency. Additionally, using lower viscosity oils helps to minimize frictional losses in moving engine parts like pistons, crankshafts, and bearings. Hybrid engines. Hybrid engines combine an internal combustion engine with an electric motor. The electric motor helps reduce fuel consumption, particularly during low-demand driving conditions. Regenerative braking is also possible with hybrid vehicles. It captures kinetic energy during braking and converts it into electrical energy, which is then stored in the battery for later use. The pursuit of engine efficiency is ongoing, with many different approaches being explored to optimize engine performance. A major goal in the recent design of a modern automobile engine is to completely flatten the torque versus speed curve and to have high torque at both high and low speeds. Some improvements merely shift the inefficiencies around, while others provide small but meaningful gains. Technologies like turbocharging, variable valve timing, and advanced combustion cycles have brought engines closer to the ideal Carnot cycle. Another area of exploration is capturing energy that would otherwise be wasted. However, big automakers are risk-averse, focusing on what keeps them competitive rather than the best solutions. They often prioritize styling and features over retooling for new engines, as their main focus is higher sales. They only innovate under regulatory pressure, like emission standards, and once they meet the requirements, major changes are unlikely. At the end of the day, the limitation is not just about better designs or materials, but about the laws of physics. No matter how advanced our engines become, we can never extract all the energy from fuel. Heat must always flow from a hot reservoir to a cold one, and in the process, some of that energy will always be lost to waste heat. It's an extremely wasteful process, and without clever devices to capture waste heat and kinetic energy, combustion engines will never be more than 40% efficient. Or they may become obsolete as electric vehicles rapidly advance and gain widespread adoption, offering significantly higher efficiency and producing almost zero tailpipe emissions. Don't forget to like and subscribe for more expert tips on engines and automotive insights.